Hi, my name is Paul Schreiber. I want to welcome you to my first bonus episode at the $25 Patreon level about what I think is the number one problem in all of electronic design. And that happens to be not an analog problem or an audio problem, but how to pick the crystals and the two capacitors for microcontroller oscillators. This is not anything new. I think this problem has been around for about 35 years. I've seen design examples all the way back to the 80s that tell you to do one thing, show you something else, and basically left as an exercise to the reader. I call this hand waving. This means that when you actually try to find information, you don't have a step-by-step procedure. You have lots of equations. I've seen app notes with 30 pages of equations that have nothing to do with real-world results. You see example after example. You pull schematics off the web. You really don't know who to believe, but there's a silver lining, and that is that it only cost about 30 cents to fix this problem, even in onesie twosies. And if you're doing something for production, you can fix this problem for pennies. Let's go find out what the problem is. So here's a typical diagram with a microcontroller, an 8 megahertz crystal, and two loading capacitors. I'll call them both CX because they're the same value. Internal to the microcontroller, you have an oscillator based with an inverter and a feedback resistor, usually around a meg. This inverter configuration with the crystal and the caps and the feedback loop is called a Pierce oscillator. Some guy named Pierce did it, I suppose. Not the president, some other guy. The solution to finding these capacitors is in the data sheet for the crystal. You will find out that all crystals have what they call a loading capacitance, C sub L. We use 18 picofarads because that's the most common for crystals in the range from 1 to 10 megahertz. If you go from 10 to 50 megahertz, this value may be slightly different, maybe a little bit lower, sometimes a little bit higher, but it will be around 18. If you have a choice, always pick 18 because the math works out easy. This is not a coincidence. The crystal manufacturers did it on purpose, and I'll show you why in just a second. So what is the mistake I talk about? Well, when people read the data sheet for the crystal, they see the word loading capacitance. They immediately think that the loading capacitors have to be the same value, which means if this is 18 picofarads in the data sheet, I should make this capacitor 18 picofarads and this capacitor also 18 picofarads. So all three of them match, 18, 18, and 18. And they say, I did it right. This is the correct answer. It's not. This is wrong. How can it be wrong? Well, let's go find out why it is wrong. Because it's wrong. Okay, so we're going to go over how you actually calculate these values for a C sub L of 18 picofarad. Well, when you see these drawings, because the capacitors are drawn side by side and they're both tied to ground, you think that they're going to be in parallel, but they're really in series. And to some manufacturers' data sheets, positive side, they will say, by the way, the value of these capacitors, or that they call the effective capacitance, are the series combination of these two capacitors. So if it's a series combination, what that means is they're like resistors in parallel, capacitors in series, resistors in parallel. So it's half the value, right? So if each one of these is 100 picofarads in series, it's 50 picofarads. So the astute observer, and I know you're astute, will say, if I need 18 picofarads, then, aha, I'll make each one 36 picofarads because half of 36 is 18 and they match up, and I'm done. Not quite. For one thing, there's no such thing as a 36 picofarad capacitor. So you have to pick 27 or 33. The other thing is there's other capacitance to worry about besides the capacitors. What capacitance is there? Well, the first thing is what we call the stray capacitance. And the stray capacitance, like a stray cat, stray capacitance is the circuit board layout. Sometimes it's how well you've cleaned the board. Sometimes it's okay if you may have said, well, it doesn't say how far apart the crystal and the caps are. I'll put them this far apart on my board. No, you have to make everything tight and close to minimize the stray capacitance. And for most boards who are designed fairly well, that's on the order of 1 picofarad. So there's 1 picofarad of stray capacitance on the board. But what else is this capacitor and crystal hooked to? The MCU maybe? Right. So the pins of the MCU also have a capacitance. They also are going to have a different capacitance if they're plugged into a socket. So you have to take that into account. Well, some data sheets will have the I/O pin capacitance as a typical with no min or no max over temperature or voltage. Sometimes they make it kind of high to me. My experience has shown the following. If you have a part that's soldered into the board, no socket, you can use about 3 picofarads for each pin. If it's in a socket, change that number to 6 picofarads. If you have it plugged into a solderless breadboard, it could be anything. I've seen stuff like 40 picofarads for an old, dirty solderless breadboard. Here's a pro tip. Don't try to run a crystal oscillator in a solderless breadboard. Sometimes you need the capacitors. It just oscillates all by itself. I wonder why. So knowing this value, all we simply say is, well, I started 36, which is the ideal value, but I'm going to have this capacitance, either 3 or 6. This is subtracted, okay? So you have 33 picofarads, right? Or you have 30. Well, this is not a standard value. You can get them sometimes, but the next nearest value is 27 picofarads. And so these are the 2 values that I recommend that are more correct than 18 by far. Because what's the series of 2 18 picofarad capacitors? 9. How is 9 anywhere close to 18? It's not. So 33 picofarads if it's soldered in the board, and 27 picofarads if it's in a socket. Now let's go see, using Mouser's website, how we can select the crystal and these 2 capacitors from the hundreds and hundreds we have available. Let's go look. So here we are at the Mouser website, where I've typed in crystal 8 megahertz into the top search box and found out there's 12,000 notifications for what that could be. So let's just make it smaller by just clicking on the word crystal and waiting. And it finds there's 5,400 different ones. Notice they're not all exactly 8 megahertz, because what Mouser does is it puts the number 8 into the search field, and so all crystals that have a frequency with an 8 in them show up in this pick list. So we have to scroll down and do one more thing, which is put 8 megahertz in there. Come over here, click in stock, apply filter. Now we have 185 left. Notice that we have a wide range of load capacitance, package and case sizes, ESRs, all kinds of things. Well, let me show you a trick. The first thing you want to do is we want to click 18 picofarad, and then we want to pick on which package we want. We'll do a radial case, apply filters. And now let's see which kind of cases we have. Well, you may be surprised to find that there's two cases to pick from. A tall one and a short one, for lack of a better term. This is called an HC49. These are called HC49S or HC49U as an umbrella. Why would you pick one over the other? Well, in a lot of older equipment, you have crystals that are large and lay flat, just like this one shown right here. And if you're doing a replacement, you want to get a crystal that's the exact same thing, although the short ones will fit into the same spot. You would get this one. But you'll also may notice there's a third lead welded on here to keep the crystal from wobbling around. So in general, there's no reason not to pick a short can. They're just as good, just as stable, and as we're about to find out, they're a lot cheaper too. So let's go up here and just say, well, I don't know which one to pick. I'll try to pick the cheapest one. So there we'll use the sort by price. And sure enough, just like I said, all the cheapest ones are in the short can. The cheapest one, which is right here, has a lot in stock. Well, let's check it and make sure it'll work in our application. So we're going to scroll down, and sure enough, it's 18 picofarad load capacitance, and it's 20 ppm tolerance. Well, that's pretty good. Usually you pay extra for that, but I can tell you right now that this company, Abracom, they will generally default to 20 ppm, where other companies like CTS and Citizen make you pay for that. So not only is this the cheapest part, it's probably the most stable part without paying a high premium, which is something in the 10 ppm tolerance and 5 ppm frequency stability. Those crystals can be several dollars in cost, and they're not going to affect your operation of your module or design. So in conclusion, this would be the crystal that I would pick. Now that we've picked our crystal, let's figure out which capacitors should we pick. So I'm going to go up to the search box and type capacitor 27 picofarad. Well, I don't want mica ones, but I'll take ceramic. Now, notice that they're all coming up in surface mount. So we're going to have to go to capacitors and pick the product and the termination style. Well, generally we want to use radial caps right here. Why it says 10 picofarad, I don't know. 27 puff. Now what voltage should we pick? 100 volts, 5%. We want it to be in stock, or what's the point of the exercise, and apply filters. And you'll see we have all these Kemet Murata. Search for the cheapest one. And sure enough, here's some TDK, which I happen to love because I'm a former TDK field applications engineer. 27 picofarads, C0G, which is a temperature coefficient, also called NPO. By the way, NPO means negative positive offset. This is the lowest temperature drift, 5%. And even if you need 2, my suggestion is just buy 10 to have for a whopping 15 cents a piece. You put these caps in your design, you'll never have to worry about temperature drift. It'll be stable, it'll start up, and it'll work every time. Now back to the whiteboard. So now I'm going to show you what I did by just simply Googling something simple like 8 megahertz CPU crystal oscillator and looking at the different schematics and app notes that are out there. Now, I didn't target anybody. I just looked. I just grabbed a few things. I'm sorry if you feel offended if this happens to be your design. I don't know. I'm just looking at stuff. But what really bothered me was some of the wording in some of these app notes. Some of them are just so horrible that it's not useful at all. And I feel sorry for people who really have a deadline, who don't know this stuff, who looks in the manufacturer's app notes and data sheets to look for insight, and it's just total garbage. The last thing I want to show you is an app note that I wrote when I was at Microchip. My boss's name was on it, but whatever. Anyway, that app note talks specifically about 32 kilohertz crystals. Now, 32 kilohertz crystals, which are used in real-time clocks, are very different than a standard crystal. They have extremely high ESR. Most crystals have around 100 ohms of ESR. 32 kilohertz crystals can have 30, 40, 50 K of ESR. Also, they have very low C sub L. The lower the C sub L, the less power they use. So if you're doing a watch, you're doing something battery powered, you want as long a battery life as you can. And one of the main ways to do that is have a low power oscillator. So check out this app note that I wrote, and let's go to the web. So when I decided on this topic, I said to myself, maybe things are different since the last 4 years I was at Microchip and I was seeing this issue all over the place. Let me just Google and see if maybe there's some stuff out there on the web that's not incorrect. So here's the very first thing I Googled when I typed in crystal oscillator MCU. Notice all 4 capacitors are 22 puff, which is great for the BOM, but it's not great for that 12 megahertz crystal. And actually 22 puff may be correct for the watch crystal. Here's the second one. Notice this is the same kind of dual crystal configuration, however it's different pin numbers, but this is very common. Again, all 22 picofarad caps. So now I'm thinking that these 2 examples are from the same family of parts, and this must have been in the datasheet or the app note, unless great minds are thinking wrong correctly. The third example I found, another dual crystal thing. This one has 18 picofarads, our classic wrong answer. Notice that the watch crystal is 12 picofarads, which would be about a 7 picofarad loading on that watch crystal, which is probably correct. +1 for the 12 puffs, -1 for the 18s. Now this one I apologize if you can't read in the bottom right corner what the values are, but I got this off of a TI website and it says can't get the LPC 1768, which is an ARM processor, again dual crystals running, does not oscillate. Well, that's because the guy has 18 picofarad on there, but he has a helpful picture to show his problem, and you know what? I think you've got more problems than just having the wrong caps there. Might want to revisit that layout. So I decided to go to the earliest thing that I could personally remember, which was this Intel app note from 1983 that talks about oscillators for microcontrollers, written by some guy, Tom Williamson, in technical marketing. Surely he's going to give us great insight, and there's lots of equations, and then it comes down to this one paragraph. Considerations about startup time and frequency suggest that it should be about equal and at least 20 puff, and they don't have to be either. What? Increasing the value of these capacitance above some 40 to 50 picofarad improves frequency stability? Yeah. It also tends to increase the startup time. No, it doesn't tend to increase the startup time. It does increase the startup time. But here's the howler, as we like to say. There's a maximum value, several hundred picofarads, depending on the value of R1, which is the feedback resistor, or which it won't start up at all. I got news for you, buddy. It's a lot less than several hundred picofarad. It's probably around 68 picofarad. So this was totally useless. I think this sets the record for the most useless thing ever published in a technical data sheet or app note. If you were an engineer in 1983 and you were just out of college and it was Wednesday and you had to have your project turned in for design review on Friday and you read this, what would you think? There's absolutely nothing here except go to the bench and plug stuff in and hope it works. Brother. So now what's our conclusions? The first thing, which is the most important thing, is always select an 18 picofarad C sub L when you pick a crystal. Now, if you're doing repair work on an older board and you don't know what the crystal is, you have no idea, here's a clue. Look at the capacitors. If the capacitors are 33 or 27 picofarad, just go replace it with an 18 picofarad C sub L. If it's some weird value like they're 47s or they're 18s, or I've seen as low as 12 picofarad, take the caps out with the crystal, put in an 18 picofarad crystal, brand new, and then put in new capacitors. If it's soldered to the circuit board, if it's this way or that way, doesn't matter. We want 33 picofarad, 5%, 100 volt. I know what you're saying right now. You're saying, Paul, it's in a 5 volt board, or it's in a 3.3 volt board. 100 volts? I pay more for that. That's extra. No, it needs to be 100 volts. And the reason is, I'm going to tell you in the next bonus episode. If it's in a socket, remember that's the lower value, 27 picofarad, still 5%, still 100 volt. The dielectric, what the material of the capacitor is made of, the dielectric has to do with the change of the capacitance over temperature. The best dielectrics, when I started growing up in the world of electronics, they called it NPO, stands for negative positive offset. Now you'll see it more as C0G, which I have no idea what that means. Somebody look it up for me and send me a little PM. But you'll see that in the Mouser as the dielectric. This is the lowest change over temperature that you can get. So that concludes our first bonus episode. Thanks for tuning in. We'll see you next time. See ya.